Alright, so I'm just getting ready for the class, getting all my devices ready, getting all the programs ready. I'm streaming at 3 different places. There's Discord, I'm on there. There is Google Meet, I'm on there too. And then there's also YouTube, and I'm just checking. I'm on there too. So there are 3 different places that I'm streaming the content to. Kind of fun. Right. And Aaron is typing. All right. Yeah, either way it's fine. I mean, Discord is mostly just for the text communication at this point, because Google Meet also has the voice. So people can either watch Google Meet and turn off the audio from Discord, or do it in any combination you guys want. Or you can also watch YouTube and then text using the Discord channel. I mean, there's a there are 2 to the power of 3 or 8 ways to do this. Exactly. Yep. Discord has the least lag time, and then Meet is next. YouTube has the worst lag time. That is true. I think everybody can listen through Discord, because we are not video sharing, because the limit is only applicable to live share screen sharing. I think for voice channel it can still handle more than 50 people on Discord. Oh, okay. I can understand that. I can certainly understand that. Well, the alternative is, we can just use Google Meet instead of Discord also for the text channel, because Google Meet has its own text channel, not nearly as flexible as Discord though. I personally prefer Discord for text, but either way is fine. Yeah, I agree. Discord text is they probably got that one down, compared to Zoom and also Google Meet. WebEx is terrible. I cannot stand WebEx from Cisco of all companies. All right, so it is time. We are actually 2 minutes past the start time of today's class. All right. So I think the first thing I'm gonna do, nope, I don't have to do it because I had it recorded already. So the lab on Tuesday, I had the solution recorded and also distributed on Tuesday, right after the end time of the lab. So I'm hoping you guys had some time to watch that and basically understand what that is about. Um, so what we'll do today is to continue with all the material.
Before you get into that,
Yeah,
could I ask a question about the lab still? I mean, I just had a question about number 3. That was it.
yeah, go ahead.
Yeah, I just wanted to know the answer.
Oh,
Yeah.
okay, I see. Let me take a look at the lab for question number 3. All right, so what is behind door number 3? All right, so this is number 3. Um, oh, so this one is just asking, in the in the logging ability, in the logging screen, what is the 5th item from the bottom without expanding anything. So let me show you guys that. So I think from now on,
Well, you know
learning
what? Actually, it wasn't this one. It must have been number two. It was the one that asked
the
me about. Yeah, this one was pretty easy.
okay, so the other number three.
The
Okay,
other number three, exactly.
the prequel of number three. You mean this one?
Yep,
Okay.
that's it.
Okay, so this one is asking, since we have a compare instruction, so the compare instruction doesn't really care whether the values are interpreted signed or unsigned. All it does is do a binary subtraction, and then it will also determine all the flags that we have talked about. So in this case, the two flags that are the most important are the B flag, which is actually known as the C flag because they are merged into one inside the ALU, and then the other one is the L flag. So now, since the branch instruction is using JCI, which means it's actually using the borrow flag from the subtractor, so now the question is, if we do end up at label L2 after this code, all three lines, what does it mean? Well, we get to L2 only if the JCI did not happen, because if the JCI happened, we would have ended up at label L1. And we can pretty much assume label L1 and L2 are different, and that is actually stated in the question as well, that they are different. So that means, if we end up at label L2, A is not less than B. Now, the question is, A is not less than B, but A is not less than B under the signed interpretation or under the unsigned interpretation. The answer is it is under the unsigned interpretation. So the correct answer is going to be this one over here, because the borrow flag is only useful to reflect whether the minuend is less than the subtrahend in the case of unsigned interpretation. For signed interpretation, we need to use the L flag. All right, so I'm catching up with the text channel. I thought I did make the video for the lab, and I thought I sent the notification through um, Canvas.
I found it in my student email.
Yeah, yeah. So
I didn't.
I think it's under the announcement of this class in Canvas. So it will reach. Oh, maybe not. What did I do? I'm pretty sure I made it. I just cannot remember how I distributed it.
100% saw it in my email.
It was in Discord. Okay, so I think Zoe is correct. It is only on Discord. So if you go back to the Discord channel on the 16th, and at the bottom, I have the solution of Q4 as a video. Yeah, this time I did not send it through the announcement. Last time I did, but this time I forgot to use that. There we go. Oh, okay. All right. Okay. Well, you can watch that afterwards too. I mean that will work as well. Because it was just an explanation of the answer to question number 4 of the lab on Tuesday. It should not affect what we do today too much. All right. So what we're going to do today is to basically start to think about high-level code using the instructions that we have talked about already. So there are a few things we can do. We can let me see what I want to do in this case. I'm debating between just kind of getting into the notes versus using a concrete example. So maybe I should do both. So I will first get into the notes so that you guys know, where you can get that material from, and then we'll use an example to illustrate the concept. So I think I'm going to do it that way. This link here is about using NVim or NeoVim along with TTPSM syntax highlighting. There we go. I had it set up before, and I think it should still be working. So I can show you what it looks like. Okay, so then you guys can decide whether it's worth your trouble or not to get that to work. It doesn't work only in Linux. You can install NeoVim in Windows. You can install it in Mac OS X. So it does install in all major operating systems. All right, so nvim, and you have to give it an extension of TTPASM. So I'm going to use test.ttpasm. TTP, once again, represents text toy processor, and then ASM is a common extension for assembly language source code. So once you get here, you can just type no op, which is a valid mnemonic. So you can see when I type it, when I type the N, it highlights it because it is not recognized as a proper line in assembly language. So until I type NOP, then it recognizes and go like, hey, I understand no op. This is a valid mnemonic. If I type another E, then it doesn't work anymore because nope is not an opcode. If I try to supply operands, like a register, it also doesn't work. So it is a very simplistic syntax checker for the assembly language that we are talking about. You can do a LD instruction, okay? So if you use the LD instruction by itself, it also highlights as incorrect because you need to supply two operands. The first operand is a register. The second operand has to be a register inside parentheses. So when everything is specified correctly, it is okay. But if you put the parentheses around the first register but not the second one, it doesn't like it. So it's kind of handy in some way. It's a very useful tool for myself because I use TTPSM a lot. So it's kind of handy that when I'm just editing, that I can spot my own mistakes. All right, so I got a whole bunch of notifications from Discord, and let me see what those things are. All right, so Vim and NeoVim are only slightly different. What I am using here, it only contains the instruction for NeoVim, but it will work in Vim as well, I believe. The color or the syntax highlighting mechanism is identical between those two. Yes, this is so to answer Marco's question, this is only for editing. In other words, this is really just syntax highlighting to make the editing of the text easier, but it does not do the assembling. You still have to go through the Google Sheet to assemble. Yeah, NeoVim means new Vim, right? So it's basically based on Vim, and Vim is based on VI because Vim stands for VI improved, and then VI itself is based on ed because VI is the visual mode of ed. Ed is basically just an editor. It's called a line editor. Ed is a line editor, which means you can only edit one line at a time. Yeah, you probably don't want to go beyond that in time because it really it's not relevant anymore. Okay. If you want to use this syntax highlighting, it only works in Vim or VI, so you do have to learn how to use VI, which does have a pretty steep learning curve. So I would say if you feel comfortable with your all of your other classes, including this one, and you think you want to invest some time to learn something that is going to be useful, because if you transfer to a UC or a CSU, there's a good chance that they would probably continue to use a Linux-like environment where VI is a built-in editor in most distributions. So it can be useful. I got some allergic reaction in my eyes again, so I'm gonna have to do something about it. It's not too bad. But if you're already tight on time, I would not get into VI because learning how to use VI, does have a curve, and it's fairly steep from what most people tell me. So I wouldn't venture into this unless you think you have time to do this. All right, so there is that. So it's up to you to decide how you want to do this. It's definitely not required. Okay, the assembler will catch syntax mistakes. Just like the syntax highlighting editor. It's just that by the time you get to the assembler, you find the errors, and then you have to go back to the editor, and you have to locate which line to edit, and so on. So it's doable, just not as optimized. So the only question is, how optimized do you want your code development environment to be? All right, so getting back to the text channel. Okay, very good. I can start a new channel or text channel just for Vim or VI. So there we go. So all the discussions related to VI can go there. So this way we don't clutter up today's lecture part of the text channel with VI traffic. So you guys can definitely talk about VI, and I will contribute too if there are questions that I can answer. All right. So the first thing we'll do in this particular module is to, well, we can always go through the purpose first. I mean, that's usually what I do. The purpose of this module is so that we can have a systematic way to convert C programs into assembly language program. And I did just say assembly language program and not really limited to TTP-ASM. So basically, the transformation of a C program into assembly language is for the most part independent to the assembly language until the very, very last step. In other words, this applies to x86 assembly language. It applies to ARM assembly language. It applies to AVR assembly language. So all the useful current known architectures can also make use of the same method. All right. So now we'll get right into it. Section 3 is about C control structures. I'm leaving out switch statements because switch statements can be done using if then else and a bunch of comparisons. So I'm not gonna talk about that one. I'm also leaving out for loops because for loops are basically while loops, but it does have initialization and also the post operation of each loop specified within the parentheses of the right after the for keyword. But for the most part, it really is the same as a basically it's a fancy while statement. So now we'll start with conditional statements. So when I talk about these things, C here is a placeholder. Block 1 is a placeholder. Block 2 is also a placeholder. So C can be any Boolean expression. It can be very complex using and or not. It can also be very simple, involving only a variable. Block 1 can be nothing. It can also be a huge number of lines of code. I don't care. It's just a block of statements, and the same applies to block 2. So given those are just placeholders, I can transform the original C code, which I would just call structured C code, into something that is not so structured. So it translates into this code here. If not C, we go to label L1, and label L1 is defined down here, which is right before block 2. And then block 1 is right after go to L1, and then go to L2 is right after block 1. So let's check, okay, to see whether the translated code is doing exactly the same thing as the original code. So in the original code, if C, we execute block 1 if and only if C is true. We execute block 2 if and only if C is false. I'm hoping that nobody needs that to be explained at this point, because after CISP310 and also 360, the basic structure of a conditional statement using if and else should be well understood. So now we get to the translated code. So we look at block 1 and we ask, well, when are we going to get to block 1? We can only get to block 1 if we do not get to, if we don't execute the go to continue execution at label L1. We get to label L1 if and only if not C is true. But if not C is true, that means C is false. So when C is false, we get to label L1. If and only if C is true, we do not get to label L1, and then we continue execution with block 1. So that means we execute block 1 if and only if C is true. Okay, so that's identical to the behavior of the original code. What about block 2? Now block 2 is right after label L1, and then right before label L1 is unconditional branch to L2. So the only way to get to label L1 so that we can execute block 2 is a direct go to or jump to L1. And that can only happen if and only if C is false, because when C is false, not C is going to be true, then we go ahead and execute the go to statement. In other words, this block of code does function identically to the original structured code, except it looks ugly, and your other professors will absolutely tell you, do not use goto, do not use labels, because that encourages spaghetti code. All right. So let me just kind of pause here and see if you guys have any questions.
I just had a quick question.
Go ahead.
So I guess is the basic idea that because with like assembly code we can only skip, is that why we have to use this sort of I wouldn't say it's like unintuitive, but sort of it doesn't feel like as much of a one-to-one.
You're absolutely correct, because in assembly code we have already talked about all the instructions in assembly code, and there's no structured conditional statement in assembly code, and it has to do with how we implement the branches and the unconditional branches in unconditional branch instructions. Now, if you're still thinking about, okay, Tech, can you talk about that again? How do we implement, how did the processor implement conditional branches? You might want to go back to the Tuesday lecture, because I actually did go through the conditional branch on Tuesday to kind of explain inside the processor how we do things conditionally. Okay. Let me see. I'm just I'm backtracking in my thought, to get back to the original question. So yes, so because the processor can only do fairly simple things, but the C construct here, the original structured construct, is actually more complex because it is designed so that we as humans can understand it more easily. It's not designed to be easy to implement in silicon. So that's why the first step is to basically make it not structured anymore. So this is structure code. You can see the curly braces, and this is what I refer to as the flattened version of the same code. Flattened means it has no structure anymore. Is that okay? So Alexander is correct. This one is designed to be easy to understand. This one is not easy to understand to us, but it is a necessary step so that we can step by step translate C code into assembly code. Alright, so Darvesh has a question. My question was basically, does the assembly look that way because we can only implement skips within memory? I suppose that's how you're referring to conditional branches, and the answer is yes. Conditional branches, are basically like a conditional goto, like this one, except the condition has to be very, very simple. So with our conditional branch, the condition boils down to, is the C flag set, is the L flag set, is the Z flag set, and so on. All right, Nathan is typing, so we have a little bit more discussion before we move on. Any other questions? All right. All right, so here's the question. There's some confusion about the question being asked because some people are using Google Meet to speak, some are using Discord to speak, and Nathan was using Discord exclusively to avoid text audio being doubled. But today's questions seem to be all asked on Google Meet. Huh. I do not know which one because I got both on, and with at least Linux, I don't have any problem having multiple applications to feed into the audio at the same time. Oh, okay. So I get it. I get it. Okay. So I'm going to echo the question, whenever I hear one, because I can hear questions from all of the channels. Well, except for YouTube, because I didn't I'm not paying attention to YouTube. Okay. All right. So the question was, so the question was, are we doing this only because in assembly code, the conditional branch instruction is very simple and it does not understand structure code like this one over here? The answer is yes. That is exactly why we have to translate the code to basically turn it from the structured manner into a flattened manner. Here we go. Yeah, so it would seem. And I think some people, I can count about 12 people or 13 people are on YouTube. So we have people all over the place. Yes, you can mute whatever channel that you don't want to hear me from, because otherwise you'll get a very disturbing echoing effect. Yeah, I'll just go ahead and repeat the question. Not a problem. Okay. Any other questions about flattening a conditional statement into something that just looks ugly, but it works the same way? All right. So if there are no questions, we're gonna move on. And I think Discord has a feature where you can talk and it will type for you. I haven't tried it, so I cannot comment on that. All right, the other half of section 5.1 looks at a simplified conditional statement where there's no else statement. So if you think about this case, it really is the same as this case over here, except block 2 is empty. I mean, that's it. That really is a conditional statement without an else block. It has an else block, but the else block is empty. So if you go through the same translation, it simply means block 2 here is empty. So that will make L1 and L2 identical, which also means this go to L2 really doesn't have to be here, because whether you have this go to L2 or not, it will continue execution at L2 anyway. So that's why when you have a conditional statement that does not have an else block, you can simplify that a little bit and simply to say if not C, go to the basically a continuation label L1, and if C is true, then you have no choice but to execute the then block. So a very slight variation of the original. If you don't want to deal with the special case and you just implement your code like this, except block 2 is empty, I'm not going to take any points off. Okay, even though go to L2 is not really needed and it does incur a very slight execution time, in this class I only care about the correctness and also about whether you understand the concepts or not. So the program being a little bit more lengthy than it needs to be is not a problem. So now we move on to section 3.2. I don't call this a while loop because in C and C++ we also have a do while loop. So I call this a pre-checking loop, because in this kind of loop, we check the condition first. If the condition is false, we go continue execution after the while statement. If the condition C is true, then we go ahead and perform block 1, and then we go back and recheck the condition C. That is the behavior of a while loop. And the translation into a flattened version looks a little bit funny, because we have to define the beginning of the loop label, which is L1 first. And then we have a conditional statement in C to basically say if the continuing condition C is false, let's go to label L2. And where L2 is basically a continuation of whatever is after the while statement. So how do we get to block 1? Well, we get to block 1 if and only if C, the condition C, is true. Because if the condition C is true, then not C is false, then it is not going to go to label L2, which means it has to continue execution at label block. At block 1. And then when block 1 is done, we have a unconditional go to back to L1, so that we can recheck the condition to see whether we can get out of the loop or not. Do we have any questions about section 3.2? All right, I'm not seeing any questions. Cool. So now we move on to section 3.3. Section 3.3, explains a loop structure that is seldom used in most programs. It is a post-checking loop, which means we unconditionally perform block 1, and then we ask, should we go back and do it again? Because if and only if C is true, we go back and we perform block 1 again. If C is false, then we get out of the loop, and then we continue with whatever is after that. You mean a post-checking loop? Post-checking loops have their place. There are certain. Okay, so since we are on this, I will explain why, in certain cases, post-checking loop do make sense. They make sense when this condition C is meaningful only after block 1 executes. So in those type of code, a post-checking loop makes sense, because you would not have a condition to check until the action is performed. There you go. Yeah, prompting user input is an interesting thing, because that applies only to only programs that makes use of the console, and most programs do not make use of the console anymore. And as a result, most programs are now most programs that interact with an end user, they are now event driven. In other words, the program sits in an event loop, and it's basically going like, okay, when the user specifies something and click on something, let me know. I'll process it at that point. So it's really no longer a loop from the programmer, from the application programmer's perspective. It is not a loop anymore. Now, I do understand what Nathan is talking about, because that applies to console programs, which basically means you're using cin, okay, to get something, and then you process it to see whether you have to, generate an error message and ask the user to input something again. So in those cases, it does make sense. What is a DBA, Chris? Oh, database administrator. Uh-huh. Yeah, that's interesting, because that is very interesting, because database people, they look at programmers, like us, and they go like, you guys don't understand anything that is quote-unquote spatial. Because a relational database, basically the whole concept of a table, the queries and stuff like that, is more spatial than it is sequential. And then we, programmers, a typical programmer, think in a sequential way. So it is kind of interesting, because a better relationship is a mutual respect between these two groups of people, because we do have different specialties. Um, so that was kind of interesting. Okay, so getting back to the translation of a do-while loop, it's actually the simplest of them all because we have a label L1 defined first, and then we have block 1, and then we have a conditional statement here to say that if C is true, go to L1 so that we can perform block 1 again. If C is false, then it will fail this condition, and as a result, it is not going to go to L1, which means it is going to continue execution with whatever is after the original do-while loop. And that's it. Wow, that is pretty simple, isn't it? So we'll do some exercise. Okay, we're gonna do a little bit of exercise here, and just to apply what we have learned here. All right, now up to here, okay, everything from in section 3 and also in section 4 does not translate into actual assembly code, which means after the translation, you can still use a C compiler and GDB to debug the program. So there's no assembly code in section 3 nor section 5, nor section 4. Alrighty. I have no idea why someone would say nothing in this class is easy as it seems. No, I'm just kidding. I know, this stuff, it takes time to digest. Okay, it really takes time to digest, and being able to clear away previous concepts as soon as possible helps a great deal. All right, so I got some questions in the text channel. All right, so that's Alexander's comment is also interesting. It's easy before the lab. So I find it kind of interesting because I have been trying to figure out something for years. When I was a student, and I'm still a student, I'm still learning a lot of things, whenever I have a chance, and I have the application. If I don't understand something, I know that I do not understand something. I can read it, I understand every single word, but in my head, I could feel that I cannot make the connections between the words in the statements, in the sentences, to things that I already understand in a very logical way. Okay, so so when I don't understand something, I have this kind of gnawing feeling that I really cannot describe, that no, I'm not quite getting this. Okay, and then what I would do, in those cases, is I would go back and look up the definitions, I would look up the examples, and then I will theorize, what the statement might mean, and then I'll design some experiments. Okay, I'll write some test code to confirm, one way or another of whether my understanding is correct or not. But I found that it is difficult to teach this, okay, to teach the way that I can figure out whether I'm actually understanding something or not. And that's why I found that comment kind of interesting. It's easy before the lab, because that seems to suggest that sometimes people don't realize that they are not making the logical connections between the concepts during the lecture, or even when they read the notes, because remember, the notes has been sitting on the server since the first day of the semester. Okay, so the lack of the logical connections between the words and the concepts in the notes does not register, okay, in some people. The lab is really, they're all about troubleshooting, and in troubleshooting, you have to utilize what you have learned, and then you have to apply that in a way that is not previously demonstrated to you. And that is how, that's why the lab is useful, because it will let people know that, hey, I think you're not fully understanding the concepts that we have talked about in class. And that's the value of the lab. Okay, at least I think that's the value of the lab. Some people may disagree and say the lab is a huge pain in the ass. I mean, that I can understand why people may feel that way, but that was not the intent. All right, so let's see what is going on here. All right, so I'm only backtracking to Andrew's comment at 6:05, and this is also why I like Discord. Is everything is timestamped at least to the minute. It's going to be relevant now. Does assembly language programming has some equivalent of design pattern? I think that's what we are talking about now. I wouldn't call it design pattern. It's not really fancy like that. It's more like a template. Okay, it's more like a template. You see this pattern, you translate that into that. You see this pattern, you translate it into that, and so on. So it's a very simplistic rule application kind of thing. It's almost syntactic. Okay, it's almost like grammatical transformation of you see this pattern, turn it into this. If you see this pattern, turn it into that. In other words, this class is about. I mean, this class like today is basically turning you into an organic. Well, assuming all of you are humans, we are. I'm turning you into an organic compiler. That's it. So that was an interesting question. That's from Andrew. And then we have Soon Gyu asking, I'm seeing the page we're watching now. Can we let me know what is the name of the page on Canvas? It is okay. So that question was answered by both Omar and David. Okay, very good. And Jackie also circled, where we are in the notes. Thank you very much. So, in case, people need to kind of time travel back to the earlier part of the lecture, you can do that in YouTube. Okay, so YouTube does allow you, when you're watching a live stream, you can actually go back to an earlier part of the recorded portion, and then you can fast forward back to the current point. So there you go. Okay, and then Luke is commenting on well, I wouldn't necessarily, use low ability, because I found it to be very common. It is a very common thing, and the other way to look at this, okay, the other way to look at this is I have constant self-doubts. Whether I look like that or not is irrelevant, but I do have a lot of self-doubts. So every time I try to formulate an opinion or a conclusion, a decision, I always go back and think, okay, is that right? Okay, is that correct interpretation, and so on. So I think, this has to do with personality type. I know MBTI is debunked, okay? But there are certain types of people who just naturally do that, okay? They doubt everything, okay? Including their own doubt of doubting. So there we go. There you have it. Alexander's comment is also interesting. It's easy to follow and watch, but when it comes time to do it yourself, so the do it part is the key. Okay, because when I designed the lab and when I designed the questions in exams, I specifically made those troubleshooting type of questions. So I'm not asking people to reapply a sequence of operations that I have done in class. So just repeat that, substitute this with that, and everything is good. I never ask those questions because they are meaningless to me. I only ask questions where it involves troubleshooting. And guess what? When people go to work in this field, I'm guessing most of you want to become a computer developer, software developer. There we go. Software developer or software engineer or someone at one capacity or another has to write code. So with all of those things, they're all basically about troubleshooting. I think the statistics was people write they create new code 10% of the time, and then the other 90% of the time they're debugging. So that kind of tells you, and debugging is a troubleshooting process. There's no set procedure to debug a program. I mean, every single bug is discovered in a different way, and it is fixed in a different way. So to succeed in this field, when I say this field, it is fairly general and broad. Being able to troubleshoot and understand concepts on the fly, and also dig deeper whenever necessary, is very, very important. All right. Okay, I get Grant's point, okay, of repetition and practice is useful, but I would practice, in from different perspectives. In other words, here's an object. So when you want to understand the object, I'm not going to look at the object from the same angle and just take repeated views of the same object from the same angle. I would look at it from this angle. I would look at it from this angle. Look at it from this angle. In other words, I want to try. I would try to get a more complete understanding of the thing from multiple perspectives. And in this class, because we're using LogicSim, so we can actually can actually design your own experiment to do exactly what I said. Okay, look at the same thing but from different perspectives. Writing some test code, okay, to find out, and then do the Control T thing, to find out, how the microcode inside the ROM is configuring all the switches and turning on the registers, or turning on the RAM and stuff like that, and make things happen. That is how we get the so-called repetition, okay? Is not to do the same thing over and over again, but to look at the same thing but from different perspectives. All right. And Luke, you are not a complete moron. If you are a complete moron, I think we are all doomed, because I'll just say there's a pretty high percentile of people out there who, yeah, I'll just leave it at that. So do not think that you are a complete moron. I mean, I can do this stuff, with more proficiency, because I've been doing this for decades, and none of you have done this for decades. There we go. Self-study is really important, and I teach this class exactly the same way to basically 60+ students. I'm not going to say this in a bad way, so don't interpret it in a bad way. But I can tell that some people, can get the same exposure taught by me, same class notes, same labs, and they understand the material in a way that is different from other people. Okay, so to a certain extent, it is an individual thing. I mean, and it also depends on how much background you have prior to taking this class. So for people who got maybe a B, a C, in CISP360, they might find this class more challenging than someone who got an A and felt really good about CISP360 coming into this class. So there's a difference, depending on the level of understanding of programming and logic prior to this class as well. I'm not trying to shift my responsibility. I'm simply stating that the entry points are different depending on the individual. All right. So I think I've distracted enough, about this. So it's time to get into an example. So let me see what example I should use. I would use tonight's lab as an example. Okay, so this is going to be a little bit helpful because we have tonight's lab using the same kind of code. It's not going to be identical, but it will be pretty close. All right. I'm gonna start up mousepad, and I'm just gonna show you, how to translate C code, like, step by step. All right, so we're talking about, taking the absolute value of x. So the way we do this, okay, at least in the lab, is something like this. I'm not really sure whether it's exactly the same or not. It might be, it may not be. All right. Overlook the lab. Preview. I don't think it's gonna help, but I'm doing it right now. Okay, so I'm only making this point so that what you learn from here may be relevant, may be applicable to the lab. Okay, so we are not going to use subroutines. Okay, we will, but not today. So we are only really focusing on the logic today. So now the first thing we need to do is to say, this looks awful, because it is using text favorite structure, which is the ternary expression. And simple people go like, why would you want to use a ternary expression when you don't have to use a ternary expression? Well, here we go. This is the non-ternary expression kind of version. And this is also the way I write code in real life. Is I basically write out the entire structure first, and then I go back and backfill the slots. Okay, in this case, the then statement and also the else statement, because this way I don't have to match parentheses or braces later on. I always know that my braces will match with the correct indentation. So here we say return negative x, because x is negative to begin with. We have to invert it, or I should say arithmetically negated, and then the other one is non-negated. All right. So now we look at this and go like, but that is still not relevant to today's code, because we haven't really talked about how to return something, okay, as in a function. Fine. Okay, so we'll make it a little bit easier. So we'll basically just say, okay, so in the end we return the value of x. So that means the code only has to put the right value back into x, and we're done. So now we have x equal to the negation of x, arithmetic negation of x, and then here we have x basically equaling to x, or if you want to, you can choose to do nothing here, but I'm putting it here, okay, just so that I can illustrate the construct. Okay, so now we are getting into something that seems to resemble section 3.1, right? So now we go, okay, let's translate this into what we have talked about in section 3.1, because we have a conditional statement. So with this conditional statement, the first thing I do is to blindly apply what we have learned in section 3.1. So we look at section 3.1, and this is why I said this is a pattern matching kind of thing, because this is the pattern that I'm describing. If what you need to translate fits into this particular pattern, meaning it is a conditional statement with a condition of C, a BLK1 block 1 for the then block, and BLK2 for the else block, like what we have in this case, then we can go ahead and transform it using this particular technique. So the application of the technique is also something that's worth mentioning, because the use of the label name L1 and L2 is really just as an example. Okay, so in real life, you have to make sure that whatever label L1 you use here is not used anywhere else. Okay, and only within this local block of code. Whatever L2 you use, same thing. Okay, is not used anywhere else, only used within the context of this block of code. So L1 really should not be used when it is time to recursively apply the same technique to block 1, because block 1 can contain its own conditional statement, its own loop, right? And then within those things can have it's a nested structure, but we only deal with one level at a time. So you have to somehow have a way to come up with names for your labels so that you don't mistakenly use the wrong label in the process. Alright, so I'm gonna take a look at the notes here. Alrighty. So what is the character limit? I think it's longer than you would want to use. I think you can use more than 255 characters for the labels for sure, because it's limited to only how long a string can be in Google App Script, which I think is going to be so long that you do not want to type it over and over again. Labels are global. Yes, that is correct, Chris. Labels in assembly language is generally global within the file. Now, in TTP-ASM, I don't have the ability to link object code, so everything is within the same file, which means the meaning of global is truly global. Okay, when you define a label, you can see it from anywhere within the program, even before the definition of the label, because in assembly language, most of the time, you can define a label anywhere. It doesn't have to be defined before the first use. Alright, so applying this technique, we're gonna, oops, wrong window. Okay, so applying the same technique, we're now going to use those things. So the first thing is we negate the condition. So I am going to do it in the most plain and simple way, which means when I mean negating C, I'm really just negating C. Okay, this time is a Boolean negation, and since L1 has not been used, I can use L1 over here. And then block 1 is really just our then block, which is X gets the arithmetic negation of itself. And then we have a unconditional goto here. So the purpose of the unconditional goto L2 is so that after block 1, we do not fall through to execute block 2. Because without this goto L2, after block 1, it will continue execution at block 2. So that's why it is necessary to have a goto L2, where L2 is basically a continuation label, so that we are basically saying, okay, let's skip to the end of this thing. And then L1 is the label that is identifying where the else block is beginning. In our case, the else block is really just X getting itself. So now can everybody see how I applied this rule in section 3.1, translating the original code, this part here, into the flattened version, which is over here. Alright, very good. So now we look at this code and go like, but that doesn't look like assembly code to me. Well, that is kind of what we're going to do today, is to turn this into assembly code. Okay? And then we look at this and go like, is there a way to kind of get rid of the negation? I mean, this negation is kind of, bothering me. I'm just looking at the time. Yes, so we can definitely have time to talk about this. So section 4 talks about what happens when you have Boolean operators inside the condition C, inside the condition that we were talking about over here, and also over here. What if this C has a negation? What if this C is a conjunction? What if this C is a disjunction? What do we do then? Well, that's the job of section 4. So section 4 basically says, after we apply everything in section 3, if you see something like this, which has a negation of C, we can translate that into something like this. In other words, if the original logic is to say continue execution at label L1 if and only if C is false, then what we translate that into is if C is true, we go to label L2, which is a local continuation label. And the only chance we can execute this go to L1 is when C is false. So in other words, this is the simpler code to read. This is the simpler code to translate into assembly code. We basically get rid of the negation. So are we good with this? Any questions? Okay. All right. What about...
That makes sense.
Oh, okay. I think Aaron just said it makes sense. So for those people who could not hear Aaron, that's all he said. He just confirmed. Okay, so moving on to section 4.2. What if the condition is a disjunction? If C or D go to label L1. Oh, that's the easier one, actually, because all it translates to is if C goes to L1, and then in the next conditional statement, it says if D go to L1. So we got two reasons to go to L1. If C is true, yes, go ahead and go to L1. If D is true, yes, go ahead and go to L1. Okay, wait, hold on a second here, Tech. Does this mean, if C is true, we don't even bother to evaluate D? Yes. Didn't you learn about short circuit evaluation in CISP310 and CISP360? Okay, I said it with a bad tone, just because I wanted to pull your legs. But I do want to find out are those concepts explained in CISP300 and CISP360 that Boolean operators or an AND are short-circuited. Yep, it is also called lazy evaluation. Yep, they are referring to exactly the same thing. The technical term is short-circuited evaluation, but we always just call it lazy evaluation. Yes, Rachel got this from CISP300. Uh-oh, Aaron does not remember, but that's okay, because this really explains why it is short-circuited. It's actually more difficult to make it not short-circuited. Making it short-circuited is the easy thing to do. Yep, but this also is the reason why in general in C and C++, when you have addition, when you have multiplication, there's actually no guarantee of the ordering of evaluation between the left-hand side and the right-hand side. But when you have disjunction and conjunction, it is always evaluating from left to right. And it is because if you flip the order of the evaluation, some program would actually stop working. So that is the reason. All right. So what about AND? Okay, because we have not, we have OR, and then this is AND. So AND looks like this. Okay, so the code that we're translating from looks like this. It has a conjunction if C and D go to label L1. And the code it translates to, that is a little bit simpler, not a whole lot, because we introduce a negation here, but we know how to deal with negation, so it's okay. So the first line says, if C is false, don't bother to evaluate D, just go straight to the continuation label L2, and we are done. Does that make sense? It does make sense, right? Because this is a conjunction. If at least one side is false, the whole conjunction has to be false, so might as well just skip the evaluation of D and go straight to label L2. So the only time we get to the second conditional go-to here is when C is true. Okay, when C is true, we are not executing the go to L2, so we continue execution with the second conditional go-to, where we would evaluate D. Now, if D is also true, then we have a reason to go to label L1, because in the original code it says if C and D go to label L1. If D is false, then we still just continue execution and not go to L1. There we go. So, do we have any questions about the translation of Boolean operators? Okay, no questions about the Boolean operators. Now, I do have to mention, section 4.4, because a lot of times you don't have to go through these transformations because of our understanding of comparisons. So when we have something that's originally like this, the negation of x is greater than or equal to y, we can just translate that into x is less than y. So we don't have to introduce extra conditional go-tos just because we are inverting a comparison. And sometimes when we have something that looks like this, if x the condition is x is less than y or x is greater than y, well, that really is exactly the same thing as x is different from y. So we can translate that without using the transformation mentioned in section 4.2 in those cases. All right, so that's theory. Now we go back to this code here and say, okay, we need to get rid of this negation. So we're going to apply this rule over here. Or we can translate the comparison. So instead of using x is less than 0, we translate this to x is greater than or equal to 0. So both are fine. You can do it either way. It's just that we can do this translation here. Alright, so I'm catching up with the text channel at this point. Would the code for L1 have to precede L2 in the case of AND? I'm not really sure what you mean by that. L1 can be anywhere. I mean, L1 can be a label before this because it is a loop label, the beginning of the loop label. Or L1 can be after this code because this is a part of a conditional statement. We don't really care. We don't care where L1 is supposed to be. We're just looking at this code here and say, how do we get rid of the AND? Where L1 is defined, doesn't matter. All right. And then next one is Omar's question. Would the AND translation also need the negation to be translated? Yes, so it has to be recursive. So now you look at this and go like, what do we do about that? Well, reapply section 4.1. So basically, it is a recursive process, where at each level of the application, you deal with the outermost operator. Now, after the application, you might end up with something like this, right? So the original AND is gone, but you ended up with a negation of one of the conditions. Then you go back to section 4.1 and recursively apply these rules until you are left with no Boolean operators. Okay, very good. Well, the code is going to be long. If you want painfully long, I have a painfully long example at the end of this module. So that's an example for people to kind of read through and follow the steps. Okay. Now, if someone says, but it's way too long, I don't want to read something like that. That is an individual decision. But I'm going to make the assumption that people are going to read it. All right. Yes, it is painfully long because if you look at the example, where is that? There we go. Section 7 is a longer example. It is basically going all the way to the end of the entire module. But every single step is just dealing with one transformation. It's one transformation at a time. So that means, if you want to, okay, this is something that you can consider doing, is to copy and paste the code. Okay, so copy and paste let's say this chunk of code into a file, and then you copy and paste the next chunk of code into another file. And then what you can do is to use a diff function you can use a diff tool. Okay, whatever diff tool you want to use, diff diff, which stands for difference. So you can use a diff tool to quickly identify the changes between the two blocks of code. I'm going to illustrate it because I think this is going to be a useful thing for some people to do, because it turns the whole thing into something that's really kind of visual, and you can focus on just the change and not so much the entire code. So it makes it easier to focus on the one thing that you should focus on. So I'm gonna use the tool, and I'll show you how to do this in Linux on the command line. And obviously this is also completely optional, because I know some of you are using Windows and you say, but I'm not using Linux. Fine, not a problem. Alright, so the tool that I'm using here is to generate, I'm going to call the first one 1.ttpasm, ttpasm, and I'm pasting the code in, like so, and stop here. And then I go pick up the second block of code, which is from here all the way down to here. There we go. So Control C, switch to the other one. Oops, wrong window. And cat to 2.ttp. Oop, okay, ttp asm. And Control Shift V. Paste. Control D. When you're done. Control D means end of file in Linux and also Mac OS. In Windows, you have to use Control Z to mean this is the end of a file from the interactive mode. Alright, so this is one way to use nvim in a kind of different way. You can specify nvim to do a diff. And I cannot remember the switch to do it. That's okay. That's what the man file is for. The man page. It's a -d. Okay, there we go. So nvim-d 1.ttpasm 2.ttpasm. So now I can compare the two text files, and it will highlight only the changes. I know I chose some color that is difficult to read, but you get the idea. Okay, you can use whatever diff tool you have, and basically just highlight the changes between the two blocks of code. All right. So I'm getting back to the text channel. Yep. On a Mac, it is Command D, which is kind of the same thing as Control D for end of file. Inside Vim, it doesn't work. But using the cat command, it does. So the cat command here, okay. So I'm just going to explain what this is doing. The greater than sign is called a redirect. So normally cat is displaying something on the console. You give it a file and it will display on the console. Okay, but in the absence of a file that you're catting from, and by the way, cat it stands for concatenation. Okay, which is kind of weird because that's not what most people use it for. So in the absence of an input file, it would use the standard in, which is your keyboard input, as the input file, and then in the absence of an output file, so it would cat it to standard out. So the greater than symbol is taking standard out and say, we are not going to display this on the screen. We are going to use some file as standard out. So the output is now captured by some file in this case. So that's kind of how it works. So anyway, back to the file that we were talking about. Back to this one, right? So now we ask, so what do we do now? I mean, how do we translate this into assembly code? So in your lab tonight, X is a register, okay? So you don't have to worry about how do we deal with parameters, how do we access parameters, how do we override the parameter, and so on. X is really just one of the registers, okay? And you can have a statement to initialize a value into that particular register. So that's kind of, it makes things easier because the focus is on the logic. How do we translate that logic? All right. So now we have to say, what about the conditional branch here? What are we going to do about this? Okay. So you can translate that into. There are many ways to do this, by the way. There are many ways to do this. The lab actually will guide you through a different way compared to what I'm doing here. Okay. So I'm going to say, but greater than or equal to is not one of the things that can be directly done using the flags. But we can do something like this. Okay. We can say, whether 0 is less than x or x equals to 0. Okay, this is a rather clumsy way to do exactly the same thing, but we can do this one, right? So now we just, I just copy and paste the rest of the code because I don't need the context of inside the subroutine anymore because we're really just dealing with the logic. All right, I'm going through the text channel, nothing related to what we are talking about here. Okay, that's good. And I'm looking at the time, we got 5 more minutes, which is also good. All right, so now we need to look at this code and go like, but now we have an OR. What do we do about the OR? So now we say if 0 is less than 0, go to label L1. If 0x equals to 0, go to label L1. So now we got rid of the OR. The rest, we just copy and paste. All right, there we go. So that means we are somehow comparing 0 and x, right? And then you go like, if x is a register, let's say x is register C, which is not the case in the lab. Okay, so do not copy and paste this code. It is not going to meet the requirement of the lab, and I do this intentionally. Yes, intentionally. So I'm going to put in comments. So do not copy and paste this code. All right, so but let's just say x is register C. So now we are basically saying, so we have to somehow compare 0 and C. Which instruction should we use? What is the mnemonic of the instruction that we should be using when we want to compare? Yes, exactly. This is why computer science people cannot spell, because we intentionally choose to use words that are so misspelled that we go like, why would you want to do something like that? What is one extra O in COMP, right? I mean, but that's the standard, unfortunately. That's the standard. All right, so now we say, so we just have to compare C and 0 and blah, 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 okay? And the moment you type this in Vim, if you turn on my syntax highlighting, it's going to say, can't do this, okay? So we'll go ahead and try that, okay? So we say nvim, you have to nvim a file with the extension of ttpasm. So we're going to have to say test.ttpasm, and now I type cmp, which register was it? I cannot remember which one I used. There we go, C0. And the syntax highlighter says, can't do this. You go like, why? So how do you get to the answer of this? Why is it not acceptable? Okay? Computer scientists are not lazy. We are just very optimized. There's a difference. Nope. Register. Exactly. Because of the 0. Okay, that is also a correct answer. So Omar and Jackie are both correct. Okay? But how do we know that? How do we know what CMP is expecting? Tech, you never talked about this. Well, I may not have talked about it, but I did give you the opcode table, didn't I? So the opcode table, you look up CMP compare, which is here. It says, CMP as a compare instruction expects two operands, x and y. And then you go like, but what is x and y? Well, according to here, x has to be one of the 4 registers, y has to be one of the 4 registers. Is 0 a register? No, right? So that is why it doesn't like it, okay? So when you go back to this code and test, so this is where the idea of, okay, so now I understand why this is not working. So the theory is it doesn't like the 0. So how do you confirm that, right? And I also find that a lot of time people don't do this for one reason or another. They don't do this. They don't test it. They don't go like, oh, so the 0 is supposed to be a register. Let me see, what register can we use here? Maybe we can just change this to register A. Okay, get rid of the 0 first and then replace it with A. Ooh, okay, that works. This is what I mean by experimenting in order to confirm your understanding. Okay, you basically just try it out, okay, and say, okay, I have this theory in my head that it means this, okay, and then you test it out, okay. Okay, so that is okay. So you have to put something in the register first because otherwise register A is uninitialized. Now you might say when we reset the whole processor, all registers are 0 to begin with. Don't make that assumption. Okay, so you always want to make sure that a register has the value that you want, even if that value turns out to be the reset value of a register. Still go ahead and initialize, okay? Because when I see code using uninitialized registers, I'm going to take points off, okay? So then what do we do? Okay, so let's go back to the code and see what we're supposed to be comparing to. Since x is register C, we need to compare to 0. So that means, whatever register I pick here, needs to be loaded with 0 first. Okay, so let's say I use register B. Okay, we have 4 registers. We have 3 other registers to choose from. So now we go like, okay, so that means I have to do something like this first. Now this is not going to work in assembly, right? Because there's no such thing as B equals to 0. So what do we do? How do we put a value of 0 into a register? What would get that done? We have exactly. Okay, very good, Marco. So Marco and Darvish, they're both correct. Okay, so we just say, okay, fine, LDI be 0. So by the time we get to the compare instruction, register B is going to have the value of 0. Cool, right? Okay. So now here's the question of, should we do this or should we do this? One way or the other. How should we do this? So we look at the original code, right? So the original code says if 0 is less than x, right? So we have to do it in this particular way. Now if you're asking, why do we have to compare BC and not compare CB? Then you have to go back to the opcode table and see how compare is done, and also how the borrow flag relates to binary subtraction. So all of those pieces should connect at this point of this class. Okay, if they are not connecting, then it's time to think about it. Okay, think about how those things connect. Okay, because it really is important to link all the different concepts that we have talked about up in this class, and be able to formulate, basically a mesh of, the concepts. Yes, exactly. We want the borrow flag to raise when B minus C is evaluated, when 0 is less than C. Because you have to think about, what is the C flag doing? What is the borrow flag doing in a subtraction? What does it reflect? When the borrow flag is set, what does it mean? It means in an unsigned interpretation, the minuend is less than the subtrahend. Now, should we be using the B flag or the C flag? That's the other question, right? Because X is signed, so we really should not be using the borrow flag. We really should be using something else, don't we? Yes, it's not about carry versus borrow. It is about borrow versus another thing that also indicates less than, whether the minuend is less than the subtrahend. Okay, so this relates back to binary comparison and also signed versus unsigned interpretation. So those two concepts, okay, are related to what flag we should be paying attention to in this case. So I'm not gonna tell you which one. Okay, there we go. David just released the big spoiler. It's okay. It's not a problem. Okay, it is okay to release that spoiler because it doesn't help in the lab. In the lab, it will guide you through yet another way to do this. So the way I'm using here is not exactly the same way that the lab is going to use, but they are equivalent methods. There we go. So we have a compare. So now what do we do? So this is where you have to understand the available instructions and be able to choose which one to use. Because at this point, we don't need any additional translation in C code, and we just need to choose the right assembly code to do this. So I'm going to use JXI to label L1, and then JYI to label L1, because there are two flags that we need to check. One to reflect whether 0 is less than x, and then the other one to reflect whether x and 0 are the same or not. Okay, I will leave it up to you guys to determine what x and y should be, which two flags should we be looking at. And then at this point, I still have x getting x, the arithmetic negation of x. And then we have go to L2. Go to L2 is fine. Okay, that's super easy. It's JMPI to label L2. And then we define label L1 over here. And you can say no up if you want to. Okay, because we are just saying x equals to x, right? I mean, there's no need to do anything. On the other hand, if you say, but I want to be true to the original C code, if the original C code that tag gives us is stupid, I want my code to be just as stupid. Okay, I cannot fault anyone for trying to do that. So in that case, we have to copy a register. Nope, LDCC is not what it needs. That LDCC is not syntactically correct. Okay, so how do we know it is not syntactically correct? Because if you do something like this, the syntax highlighter will tell you, can't do that. Because LD is always loading from a memory location. The second operand, the register that you specify in the second operand is specifying, oh, this register will tell you where in memory we're going to grab the actual value to overwrite register C. So LD doesn't do the trick. So what do you think is going to do the trick? Okay. No, they're not exactly universal, but I'm following the standard used by most assembly language. Sort of. Okay, so looking through the opcode table, okay, we need to know how do we copy a register to another register. So which one should we be using if I want to just copy a register to another one? Exactly, CPR, copy register. That's exactly what we want. Where am I supposed to go? There we go. So we're going to use capital public radio. Which register again? It's in CC, right? There we go. And then we have label L2. Now we have it done. Well, not really, because I haven't really quite explained how to do this. How do we take the arithmetic negation of a register without using another register? Flip the flip the bits. Well, you flip the bits and then you have to do one thing, right? I mean, it's not just flipping the bits. If you're only flipping the bits, it's called one's complement. What we want is two's complement. So now you have to remember how two's complement relates to one's complement and what instruction we should be using in this particular TTP-ASM language to accomplish that. There we go. Nope, Darvish, that's a logical NOT. We are not using a logical NOT, we're using a bitwise NOT. There we go. Yep. Tilde C is bitwise NOT. There you go. Okay, that's fine. Yeah, I just want to kind of point that out so that people understand we are not performing a logical NOT, we are performing a bitwise NOT. Okay. All right, so we are running out of time. The lab is already released. I need to give you guys the access code to it, and then you guys can go do it. Okay, so remember, this is really just an example using the same code that I use in the lab, but the approach is different. The lab will guide you through a different approach, so don't try to follow this as a track. Okay, I compare the mind as a vehicle, and instead of trying to follow a rail, okay, going to a particular place, try to imagine your mind is a dune buggy, okay, and you're in a desert. That is useful in a class like this. Okay, don't think about your mind as a train on the rail where you just kind of keep going and occasionally you have switches. Nope, your mind is a dune buggy in a desert. All right, so let me go look up the code of today's lab. Yep, it is. Yep, I think it's ABS. I think Victor will make a very good hacker because he can he can anticipate, what word I will be using as the passcode. And of course, a dictionary attack will probably find it too. I say these things and laugh at the same time because why would anyone spend energy to try to hack my lab to get into it earlier than I actually release it? Well, maybe just as a challenge, because tech says, oh, why would anyone do this? And then someone is going to say, I would do it. Yep, so it is indeed lowercase ABS. That is correct. There we go. And I'm going to pin this so it's easier for people to find. Alrighty. Okay, so I think we are ready to kind of move on to the lab portion. I'm going to step away for a few minutes, grab something to eat, and I'll be back to answer questions. Before I go, I got one message already sitting, in the DM area. So I'm going to go answer that question, and then I'll be back. Well, thank you. Thank you, Tom. It's not going to be a meal. It's going to be more like a snack. Cheese puffs. Cheese puffs. Alrighty. There we go. Yeah, nothing fancy like that. It's really just cheese puffs from